So now we are going to discuss about the next process, which is cooling and dehumidification. Now, how does this process of cooling and dehumidification takes place? First of all, let us see how it looks like. So the process of cooling and dehumidification takes place along line 1 to 2. As you can see here on the psychrometric chart, this is dry bulb temperature and this is specific humidity. So process which is taking place from point number 1, this is the initial state of the air and this is the final state of the air. This is cooling and dehumidification. How it is cooling and dehumidification? If you will see here, this is the temperature T1. This is the initial dry bulb temperature of the air. This is the final dry bulb temperature of the air, and you can see that the value of T2 is less than T1. So that means this is the process of cooling. And simultaneously, if you will see here, then this humidity or specific humidity is W1, whereas the specific humidity at this particular point is W2, and we can see that W2 is less than W1. So we are removing the moisture from the air also. So it is dehumidification. So basically combined, we can say it is a process of cooling and dehumidification, and it can be carried out by the following equipment. Now you can see here we have shown a duct here. This is the duct which is carrying a cooling and dehumidifying coil. It is also known as C&D coil at a temperature Ts. So Ts is the surface temperature of the coil. So it is surface temperature of C&D coil. And one thing I would like to tell you that the temperature Ts is less than T1, and moreover Ts is also less than TD1. TD1 is the dew point temperature of the incoming air stream. So TD1 is the dew point temperature of incoming air stream. So when the air passes over this cooling and humidifying coil from state point 1, it reaches at state point 2. So it comes out at state point 1. So what happens to the various properties? So you can see that the final dry bulb temperature is less than the initial dry bulb temperature. Final specific humidity W2 is less than the initial specific humidity W1. Relative humidity actually has increased, though the value of the moisture specific humidity has reduced, but the value of the relative humidity has increased. This we will see in the psychrometric chart also. And simultaneously, since we are removing the heat, so final enthalpy is less than the initial enthalpy. So this is how this process takes place. So what is the condition for cooling and dehumidification? I have already told you the temperature of the coil. See, this is the coil here. Okay, its surface temperature is Ts, and that Ts is at this particular point. This is the temperature Ts. So you can read this temperature from here. This is the Ts, or you can read it from the dry bulb temperature line also, wet bulb temperature line also. So it is equal to, let us say this is the T2. So T2 temperature is also the, you can say the apparatus dew point, or the uh, effective surface temperature or the average surface temperature of the cooling and dehumidifying coil. So you can see this particular temperature is less than the dew point temperature of the incoming air stream. This is the incoming air stream temperature at T1, and its dew point temperature is here. So actually the process which is followed is like this. First of all, the air is cooled from state point 1, it goes up to this particular point, and then it follows this particular path and reaches at this particular point. So effectively I can say the process is first from 1 to, let us say, A, and then up to point number 2. But actually if we join the point number 1 and 2, then we can show the process to be taking place along this particular line from 1 to 2. Otherwise the process happens in this manner. First it goes along this direction and then it goes along this particular direction. So this is the condition that the average surface temperature of the cooling coil should be less than the dew point temperature of the incoming air stream. So Ts is the average surface temperature of the cooling and humidifying coil. It is also called as ADP or apparatus dew point temperature. In this case, we have considered the bypass factor of the cooling and dehumidifying coil is 0. Therefore, T2 is equal to Ts. So you can see the final condition is lying at the same value as that of the apparatus dew point or the average surface temperature of the cooling and dehumidifying coil, because we have not considered any value of the bypass factor. If we will consider that the bypass factor is equal to zero point 0.1, now let us consider this. Then the value of T2, this is the final condition now. This is the final condition of the air. This temperature is will be a little bit higher than the apparatus dew point of temperature of the cooling coil. This is TADP. And then we can define the bypass factor as what it is known as. It is actually equal to potential unutilized. Potential unutilized divided by potential available. So potential unutilized is this temperature difference. This temperature difference, which is equal to T2 minus TADP or TS. And the potential which was available to us was from T1 up to TADP. So this is the temperature difference which was actually available, which we could have achieved in this process. So bypass factor is given by T2 minus TS divided by T1 minus TS. And this TS is nothing but TADP, apparatus dew point of the cooling and humidifying coil. If we want to define the efficiency, we can define the efficiency by the formula. Efficiency of the cooling and humidifying coil is equal to potential utilized divided by the potential available. So the potential utilized is actually T1 minus T2 divided by T1 minus TADP. So I am unable to write it here. So I will write it here. Efficiency is given by T1 minus T2 divided by T1 minus Ts. And if you will see, then this value of the efficiency is always equal to 1 minus bypass factor. You can try and you will find that the bypass factor and efficiency are related by this particular equation. And this process is particularly carried out in case of a window AC. You know, in case of a window AC, what happens when the air comes in contact with the cooling coil of the window AC, the moisture is removed from it. You must have observed that the water is coming out from the back of the window AC. So that is the condensation of the moisture which comes in contact with the coil. And simultaneously, you know that there is cooling of the air also. So you can see this is the condensation part which is taking place. So it is equal to W1, this is equal to WA, and the difference is W1 minus WA. So this is the condensation part, and this is the sensible cooling part because the temperature is reducing from TA to T2. Okay, so this is the sensible cooling part, and this is the latent heat removal or the condensation. And this is the, you can say, this is the apparatus dew point of the cooling and humidifying coil, or the surface temperature of the cooling and humidifying coil. And you can read this value from here. So this is Ts or TADP. Now you can see in this particular case we are removing both the heats. The first heat is the latent heat, which is can be shown like this, and this is the sensible heat part from here to here. This is the sensible heat removed, and this is the latent heat removed. So this can be said that this value is equal to QL, and this value can be said as QS. Here the value of enthalpy is H1, here the enthalpy of is HA, and here the enthalpy is H2. Okay, so I can say the total heat removed QT is equal to sensible heat plus latent heat removed. So I can write that it is equal to MA into H1 minus HA plus MA into HA minus H2. So this is the sensible heat part now, and this is the latent heat part. And if you see this value of sensible heat removed HA minus H2, then it is given by 0.0 0.0204 cmm into delta T plus 50 cmm delta W, this much kilowatts. And we can also say that it is equal to, you can take cmm as common, so we will left with 0.0204 delta T plus 50 delta W in the bracket, this much kilowatts. Otherwise, if I want to write this particular value of the heat removed from the air, then I can write this is equal to mass of the air into H1 minus H2, and this value will be equal to 0.02 cmm delta H, this much kilowatts. So you can see it here, I have derived this expression here also. So it is equal to total heat removed, Q is equal to total heat removed, it is equal to MA into delta H, MA into delta H is equal to H1 minus H2. So the value of MA is given by rho into cmm into divided by 60, and it gives us a value 1.2 into cmm divided by 60 into delta H, this much kilowatts, it is equal to 0.02 cmm delta H. So this I have derived in the previous slide also. So in which season we should use cooling and dehumidification? It should be used in rainy season. In summer season we use cooling and humidification, but in case of rainy season we go for cooling and dehumidification process, because in rainy season the humidity is quite high. That is why we will have like to go for dehumidification as well as cooling in case of rainy